Folks, I'm about to tell you something that's going to break your heart. And it's that this is the last video for a while, because this is the last part of 5.4, which is the last section that's going to be on the quiz. Remember, your quiz coming up is going to be on sections 5.1 through 5.4, so this is it. The second half of 5.4 is actually pretty short, so what I'm going to do is I'm going to finish up talking about altitudes and orthocenters, and then I'm going to go into some review problems, because why not, right? Why not make the most of this video? So, the last of the segment things that end up going through triangles is an altitude. So you already know what an altitude is, actually. You probably just know it better as the height of a triangle. So if I'm looking at this guy on the right, a height would pretty much be this. This is an altitude. The thing that makes it a height is that it goes from a vertex of the triangle to the opposite side and is perpendicular to it. We need both of those things to be true. It needs to be perpendicular to a side of the triangle and go through the opposite vertex. So considering that the height is such a famous thing for being part of the formula for the area of a triangle, we know that the area is base times height. But really what this means then, based on the definition of an altitude, is that there's actually three of them. So do me a favor and rotate your iPad. Let me do that better. Rotate your iPad such that this orange segment that I'm highlighting is actually horizontal to you, because that's how I'm going to be writing. So, check this out. If you could read this, you're doing it right. It says hi. That's a base, and this right here that I'm drawing, maybe I could draw it better than that, this thing that I'm drawing is a whole other altitude in this triangle, because it's going through the opposite vertex, and it's perpendicular to a side. So what I can see here is that this is a height, and the thing on the bottom that I started with is a base. That's fine. But it's going to be the case that this is a different B and H than previously. So the weird thing here is that this B and H, though different from the first B and H, can both be used to find the area of a triangle. Imagine it like this. Imagine I find the area of a triangle the first time around, and it has a base of 6 and a height of 2, right? And then I rotate the triangle, and I try to calculate the area again, and I get a base of 3 and a height of 4. Well, both of those times, whether it's 6 and 2 or 3 and 4, the area of the triangle is going to give me 6, because 1/2, 3 times 4 is 6, 1/2, 6 times 2 is 6. So I don't need the same base times height in order to get the area of the triangle. A triangle is going to have one area regardless of the base and height I choose to use. So you're going to sometimes be placed in situations where you have multiple bases and altitudes to choose from. If you want to calculate the area, just choose whichever one's most convenient. Got it? Neat. So as far as the orthocenter goes, of course, the altitudes are going to be concurrent, which means they're going to meet at some point, and that point happens to be called the orthocenter of a triangle. So here's my junky little drawing where the orthocenter is right in the middle of those. It's better done on the whoa, that was a bad point. It's better done on the bottom here where the orthocenter is P. So of course there might be some interesting facts regarding it being inside, outside, around the triangle, or it could not be, right? The incenter and the centroid were always inside, so maybe that's the case with the orthocenter too. What I'm going to do is I'm going to flip to the 5.4 sketchpad document on orthocenters, and I'm just going to point my iPad at the laptop and show you what that's like. So here we are, the document that says orthocenter. There, sorry, that was my finger. There it is right now, kind of sitting in the middle of this triangle. This triangle appears to be acute, right? Everything seems to be less than 90 degrees. If I were to shimmy this around, I see that if I move this thing to the, well, the closer to equilateral this gets, the closer to, however we define the dead center of the triangle to be. But as I move this point to the right, as the triangle approaches, actually, with this guy, approaches being a right angle, we can see the orthocenter kind of creeping towards that vertex until it actually is, finally, a right angle. So it looks like when it's acute, it's inside the triangle. It looks like when it's obtuse, it's, sorry, not obtuse, when it's right, it's on the triangle, most specifically on the vertex of the right angle. And if I go, it looks like if I go, can I possibly fix this? If I make this thing obtuse, it looks like the orthocenter, the more obtuse I get, the further away it starts creeping. See? Goodbye, orthocenter, venturing into the bottom right of the screen forever away. So I guess that wraps that up. Let's go back and check out some of these, let's record our findings, I suppose. So, if it's acute, it's inside the triangle. If it's right, it's, and let's get as specific as possible here, on the vertex. I'm still garbage at writing on this, by the way. On the vertex of the right angle. And if it's obtuse, it's outside. This handwriting's so bad, I apologize. So keep in mind that you can also play around with the sketchpad as well and come to these conclusions yourself. And it's just fun to tinker with. I saw you guys do it in class today, and people seem to enjoy it. So let's try some practice problems now. When I say try some practice problems, I don't really mean you watch me do it. What I mean is, you should probably pause as soon as I'm done with the sentence and give the problems a shot yourself, because I'm going to take a pause myself for about 3 seconds to give you a chance to do it. Ready? Go. Alright, I think that's sufficient. Let's actually go at these problems now. So if I want to find AC in this triangle, well, what I should probably notice is a lot of things are congruent in here. I see a 2 and a 2, I see a 5 and a 5, and I see if I put the 2 and 2 together, and the 5 and 5 together, I get I get F and G being midpoints as well. It sure does look like there's a bunch of mid-segments going on in this problem. So what I could say then is that DE, because BE is congruent to EG, and DB is congruent to FD, I could say that DE is a mid-segment of triangle FBG. Ooh, that was bad. Let me try that again. Not much better, but you get what I'm getting at here. So, seeing as DE is parallel to FG, it's going to be half its length as well, which puts FG at 8. So, let's try this out too. Let's look at the bigger picture now. If I want to find AC, I can probably guess that FG is the midpoint of that. Let's confirm that real quick by acknowledging that this is 4, as is this, which makes G a midpoint. And BF is congruent to AF, because they're both 10. Which, yeah, does in fact confirm that F and G are midpoints, which makes FG a mid-segment of AC. So I guess FG is half of it, which makes AC 16. Nice. Problem done. Bottom left, I suppose. Determine if we know that BC is equal to BD. This problem looks like it comes from section 5.3, which is related to angle bisectors. But even then, if we didn't know anything about that, we could probably try to show it with triangle congruence. So in this case, we don't know that AD is an angle bisector. We don't know. And we also don't know if BD is the shortest distance. Is BD is equidistant. Oh my gosh. If BD is congruent to DC, meaning that D would be equidistant from the sides of this thing. We would need a couple things to actually show that that's true. We would need to know, well, the right angle is in the wrong place. It would have to look more like, I'm going to sketch it. It would have to look more like this. For a point to be equidistant from two sides, that shortest distance would have to be perpendicular to it. So in this case, this is like bottom 5 worst drawings ever. But you see what I'm getting at here. In order for D to be equidistant from the sides, that would imply that these distances are perpendicular to it. Because remember, the shortest distance from a point to a line, or line segment even, or array or whatever, is going to be a perpendicular segment. So in this case, we would note that that's true, but we're lacking some vital ingredients right here. So we just don't know. Bummer. The one below it. So we see that D is on the angle bisector, which would imply that D is equidistant from the sides, but we don't know if if BD and DC actually are the shortest distance from each side, right? Because the shortest distance would imply perpendicular marks, and we don't really have that. In fact, if I were to actually prove this with triangle congruence, I have a pair of A's, that's neat, I have the reflexive property, it's an S, and then I kind of fall short from there. So it's not even like I could show congruence and then use CP/CTC. It's lacking. It's a bummer. It's another I don't know. Starting to wonder what we do know here until we get to the last one. We can see that D is on the angle bisector. The shortest distance from D to the sides is BD and DC respectively, because they are perpendicular. Therefore, yeah, we can conclude that those distances are the same. Awesome. And even if we didn't know, like, pretend you just didn't watch the 5.3 video, which might tragically be true for some of you. What we could do is we could actually show, because of S, that these two triangles are congruent, and then just use CP/CTC to get this as a result anyway. So it's totally possible using the old skills we had in our repertoire anyway. This guy on the top right now, I like it. So to go from R to the origin is a distance of h. To go from the origin to point Q is also a distance of h, which would imply these segments are congruent to each other. Also, since we're on the x and y axes here, which are perpendicular to each other, we can show the reflexive property to show that this right triangle and this left triangle are congruent to each other. Then we could use CPCTC, blah, 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 to show that these two sides are congruent to each other. So at the very least, let me erase everything that's unnecessary here. We could do that at the very least to show that it is isosceles. We have that. We don't know, however, if RQ is congruent to PR and PQ. We see that this bottom base has a length of 2h, whereas these well, not horizontal ones. These lines like PR and PQ, well, I guess we could find their lengths by using the Pythagorean theorem, because this is a distance of h, and this is a distance of, sorry, that's a distance of k, and this is a distance of h. Boy, that's an annoying number that's not equal to 2h, so as far as we know, depending on the value of k, this thing is at the very least isosceles. Maybe equilateral if we knew some more information about k, but since we don't, the best we could do is call it isosceles. Remember that an equilateral is a type of isosceles, so it's a more specific classification if we can actually do it and prove it, but we can't in this case. The best we could do is call it isosceles because this is h, that's h, and triangle congruence yields the fact that PR and PQ are congruent. Neat. This bottom right guy goes back to section 5.2, I think, because it looks like, based on the fact that D is a midpoint, and this angle is right, that AD is a perpendicular bisector. Cool. Since A is on the perpendicular bisector, we've shown this before, the perpendicular bisector theorem says that AC and AB are going to be congruent, because A is going to be equidistant from the sides. That lets me set up this equation where I can solve for x. So while I'm doing this basic arithmetic, remember that I'm not going to give you any proofs that are going to ask you to actually remember terms like perpendicular bisector theorem or whatever. That's just tedious. It's more important in this section that you actually know how to work with these things to solve. So in this case I did solve and I got that x equals 12. If I want to find the perimeter I need to find AC, NCB, and BA, which means I have to plug the stuff back in. So, boy, I gotta find room to do this because I wrote too big. AC is equal to 3 times 12, which is 36, minus 6, which is 30. Just to check, I mean, I know these are congruent, but if I did it right, it should be the case that if I plug x into here, I get the same answer, which I do. AB ends up being 12 plus 18, which is 30. Good, they're both 30. And I know that CD is 8, and because that's congruent to DB, I know that that's 8 also. So the perimeter is going to be equal to the sum of 30 and another 30 and 8 and 8, which is 16. So 30 and 30 and 8 and 8 is 76. Running out of room a lot here. Good. Moving on to the next page, one final note for this section. This is interesting. Show that in an equilateral triangle, the circumcenter, incenter, centroid, and orthocenter are all the same point. We're going to do that in this case. By the way, L-I-M-E spells... come on. L-I-M-E spells lime. Yay. We're going to show that this is the case by starting with LM and showing what kind of segment that is. Let's suppose we construct any point LM here such that any line segment LM here such that it is an angle bisector. Cool. So we'll call this 30 and 30 degrees, and the rest of these are 60, because we started with an equilateral, which implies equiangular, which in terms of triangles means that it's going to be 60 degrees. So if I bisect a 60, I get 30s. Neat. So we also know that it's equilateral, which would imply LI is congruent to IE and EL also. Cool. So let's see what kind of things we can conclude here. It looks like, oh, well, I could do this. Whoops. I could show that LM is reflexive to itself, but it kind of looks like I don't even need to do anymore. Based on a lot of things here, I see, hang on a minute, let me switch colors. I see an A and an A. I see a second pair of A's, and I see a pair of S's. 2 pairs of S's, actually, if I include that. So it sure does look like triangle LIM is going to be congruent to triangle LEM. Either because of, I don't know, it looks like ASA or maybe SAS, depending on which ingredients I choose to use. I have more than enough, which is awesome. So from there, what I've basically shown is that this left triangle is congruent to this right one. Nice. So as far as what that actually does for me, that does a bunch of stuff. I could say, because of CPCTC, these things are congruent to each other, so I'll call them both x. And they're also supplementary, because of the linear pair postulate. So if x plus x equals 180, as we know is the case because of the linear pair postulate, we know that these guys are right. We know that x is 90, so we know that these are right angles. I'm just going to erase as I go, because this is going to get more and more profound. Because of CPCTC, I also know that IM and ME are congruent. Again, that's because of CPCTC, between this left guy and this right guy. So that kind of teaches me something about the segment LM. I started off showing that it is an angle bisector. I'm too lazy to write out the word angle. Angle bisector. What I've just shown here is, since it's perpendicular to a base and bisects it, it's also a perpendicular bisector. What else? It's going from midpoint to a vertex. M is the midpoint and L is the opposite vertex, so I guess that means it's a, oh my gosh, median. And it's going from a vertex to the opposite base. That makes it an altitude too. Holy smokes, it is every single one of the things that we've shown in the last 4 sections, except for mid-segment, but that's a weird one anyway. So it sure does look like, if I were to rotate this triangle and do it all again, which I'm not gonna, but I could, if I were to rotate this and do it again with, say, hang on, let me pick a different color. Really should have paused it for all that. Start with LE, and then draw an angle bisector from I to, I don't know, what's another point, J. Well, I can show the same thing, which is that this would be an angle bisector, perpendicular bisector, meeting altitude as well, and they would meet at this point, whatever point that is. Since it's the point of concurrency of all of these things, that makes it every single center point that we've had. So if I have an equilateral triangle, folks, if its angle bisector is the incenter, the circumcenter, the centroid, whoops, and the orthocenter are all the same point. So that on its own has some interesting properties that we don't have time to explore. This video is getting long anyway, so I recommend, I'm just going to remind you, that you have some, you have a review sheet, 5.1 through 5.4 Centers Review, I think it's called. It's in your backpack, and if you find yourself with a lot of time, I would not only look at that, but I'd look at the construction worksheet as well. So if you're finding yourself, like, not knowing what to do now, I suppose you could always come around and ask me for help, but this is it. This is pretty much all you have to be responsible for the 5.1 through 5.4 quiz. So, thanks for watching. 5.5 will come in the near future.